5.5, we look at another use of a normal distribution, and that's to approximate binomial distributions. So we did binomial distributions in the past. Remember, with a binomial distribution, you have n repeated trials that are identical. You have a probability of success, a probability of failure, and then x is the name of your random variable. And we're looking for the likelihood of having greater than or equal to so many successes, or just what is the likelihood of a certain number of successes or fewer successes and so forth. So we're just looking for what is the probability of being successful. So if we only have, let's say, 6 trials, and we want to know what is the probability of having greater than or equal to 4 successes, then remember the way we do that. We find out the probability of having 4 successes, the probability of having 5 successes, the probability of having exactly 6 successes, and we add those together. And if we're only going to 6, we just do those 3 calculations, sum them, and that's our probability. But keep in mind also that just one of those has a fairly lengthy formula. We have to do how many combinations are there of having x successes if we have n trials, and then we have x successes and n minus x failures. So there's a lengthy calculation that we have to do for each one of those, and it involves factorials. We can do that, and if we have 3 of those, we can do each one of those and add them together. But imagine that n was 60, and that we were looking for the probability that x is greater than or equal to 41. Then we would have to find what is the probability that x is 41, and 42, and 43, or 44, or 45, all the way up to 60, and add those together. And that would take quite a bit of time. So instead of doing that, sometimes we can use a normal distribution to approximate the area of the binomial, or the probability of the binomial probability. So our PowerPoint tells us that in order for us to be able to use this approximation, n times p has to be greater than or equal to 5, and so does n times q. If either of those products is not greater than or equal to 5, then we can't use the distribution. So let's look at that and see why. Here we have a binomial distribution where we have 18 trials. The probability of success is 0.2. The probability of failure is 0.8. And this is our distribution table. These have the different values of our random variable from 0 up to 18, and these have their corresponding probabilities. And here is a graph of that probability distribution. Notice, for the most part, that almost mirrors a normal distribution, but it is skewed a little bit to one side. If we did the calculation n times p, we would get 3.6. Or if we did the calculation n times q, we get 14.4. Since this one is not greater than or equal to 5, then we can't use a normal distribution as an approximation. Our binomial has to closely resemble a normal curve in order for us to use this method. But notice, if our p increases, now if our p is 0.4, n times p and n times q are both bigger than 5, this distribution much more closely follows a normal distribution. Remember that the mean of a binomial distribution is n times p, so the mean of this is 7.2, so around 7, that's the mean, and pretty close to being symmetric. Not exactly perfect, but that's why we call it an approximation, not an exact. Notice if we drop down to, let's say, n equals 8, if p is 0.5, that's very symmetric. But still, even though it's symmetric, n times p is not 5, nor is n times q. If we drop down to a small p, that's really skewed to one side or the other. If we bump p up a lot, that's skewed the other way. So in this case, notice n times q is nowhere close to 5, so we could not use a normal distribution to approximate what's going on because this distribution doesn't have that bell-shaped curve. If we bump this up to, let's say, n is 26, that's still skewed a long way to one side with this p and q because look at n times q. It's nowhere close to 5. But if we adjust these values to where n times p and n times q are both 5 or more, yeah, we have some lower values here, but in general, that's pretty much a bell shape. Notice the mean n times p is 18.2. Where does the mean look like it is? It looks like it's right around here, right around 18. And that's pretty much bell-shaped symmetric. Now, just in case you haven't picked this up, each of these bars is the probability for this number of successes. So if we looked at what's the probability of 17 successes, the probability of exactly 17 successes is 0.14307. The probability of exactly 18 successes, that's 0.16691. So these bars are the corresponding probabilities for each of these values. But keep in mind, for a binomial distribution, this is a discrete distribution, meaning there are gaps between our numbers. Where when we're talking about a normal distribution, it's a continuous distribution. There are no gaps in between our values. But still, we can use the fact that this is approximately normal, and also remember that for any probability distribution, if you add all of the bars, add each probability, they add up to 1. So if we used a curve, let's copy this over. That's a little big. Notice that's fairly normally distributed. If we wanted to know what is the probability that x is greater than or equal to 20, instead of having to add up the column for 20, 21, 22, 23, 24, we could find the area to the right of there, and that would encompass all of those bars. So instead of adding each of those areas of those rectangles, we could add the area underneath that curve, and we can find the area underneath that curve from our normal distribution table. The question is just, if this is our binomial probability that we're looking for, how do we translate that into a comparable normal probability that we would be looking for? So let's just work through some of the homework and address some of these issues as they come. Okay, so let's start with this one. For each binomial probability statement, I'll take on some more question. Determine the corresponding normal distribution probability statement after continuity correction. So we're not going to go into all the details, but if we're looking for a probability of x being greater than a number, or the probability of x being greater than or equal to a particular number, and these are binomial, keep in mind that these are discrete values. So if we say greater than 100, that means 101, 102, 103, etc. If we say greater than or equal to 100, we mean 100, 101, 102, etc. So there are gaps between our numbers, and depending on whether we include our number or don't include it, that's going to affect which one we start with. So to address the issue that there are gaps, when we convert that to a normal distribution, we do what's called a continuity correction. So we either go a half unit above or a half unit below this value to start adding up or to accumulate our area. So for one of these, we would do x is greater than 100.5 perhaps, or x is greater than 99.5. Why those numbers? If we're on a number line at 100, if we go a half unit above there, part of this goes to the fact, we're not going to go into all of these details, but that for any continuous distribution, we can't find, it's not possible to find the probability of x being one specific number. Because for a continuous distribution, we're looking for an area. But if we're looking for a specific x that has no width, you can't have an area that has no width. So we can go from somewhere to somewhere. So if we were looking for 100 and a binomial, not greater than 100 or not greater than or equal to 100, if we were looking for exactly 100, we would want to actually go for a normal distribution. To make sure that we include that, we would go from a little bit below to a little bit above. Notice that width is 1 unit, and x equals 100 is halfway in between there. So that's what's called a continuity correction. It gives us the same width, and it is centered at whatever x value we're dealing with. So where it gets confusing is, when do we go a half unit past? When do we go a half unit prior? So for this one, do we need to start at 99.5 or do we need to start at 100.5? Notice if we're looking for the probability that x is greater than 100, binomially speaking, that starts at 101, then goes to 102, then 103. So a half unit less than 101 would be 100.1. So this is the probability, normally speaking, that would correspond to that one. If we were doing the probability that x is greater than or equal to 100, we want 100 to be included. So if we started at 100.5, part of 100 has been excluded. So we would start at 99.5 so that by the time we accumulate everything to the right, 100 has been included and all of the values to the right of 100. So if we look at our example, let's copy these. We're going to find out which one of these go together. So if we're looking for the probability that x is less than or equal to 104, and that's a binomial distribution, then we need to include 104, 103, 102, all the way down to 0. So the question is, if this is 104, do we need to go a half unit below it or a half unit above it? Well, if we're doing less than 104, we're going to be doing on this side of 104. If 104 has to be included, then we don't stop here at this correction. We stop here at that correction. That includes 104. So if we make our continuity correction, then for a normal distribution, we would have to go from 104.5 and everything to the left of it. So this, let's see, I'm sorry, we don't use the equal, so this is the one for number 5. All right, so let's do this one. If we want to do the probability that x is just straight less than 104, then that's not going to include 104. That's going to include 103, 102, and on down. So if we're at 104, we either continuity correct a half unit to the left or to the right. Our probability is going to the left of 104, and we don't want to include 104. We want to only include 103. So if we went to here, that would include 104. If we stop there, it doesn't. So in terms of a normal approximation, we would use x is less than 103.5. So that would be this one. For number 7, probability that x is greater than or equal to 104. So that includes 104. So that's 104 and to the right of 104. So do we use a continuity correction this side or that side? If we're going to the right of 104, we're doing all of these. And this time we want to include 104, so we want to go to here. So that would correspond to the probability that x is greater than, if we go a half unit to the left, that would be 103.5. So x is bigger than 103.5, that's 7, so that would have to be 8. So why would that one be 8? If 104 is not included, we wouldn't want to go this far, so we would correct to there a half unit, so that'd be 104.5 and bigger. All right, so that's how the continuity corrections work. So let's look at an individual statement and dissect it. So we have a given binomial probability. So let's write this probability in words. So P, the probability that x is greater than or equal to 108. So that's the probability of getting if we say greater than 108 or equal to 108, that means at least 108 successes. It's not just exactly, it does include exactly, but it's also more. If we said more than does not include 108. It's just strictly what's bigger. So at least means 108 or more. So we want to find out which of these statements for a normal probability corresponds to that one for the binomial. So what normal probability corresponds to this binomial? So if we look at a number line, we're either going to correct a half unit to the right or a half unit to the left. We're including what's bigger than, so at least 108. So if we're doing at least 108, then 108 has to be included. So if we stopped here, 108 would not be included. But if we go all the way to there, it is. So we would have to correct a half unit to the left. So in terms of a normal, we would use 107.5 or bigger. So bigger than 107.5 includes 108. All right, let's do one that actually has two components to it. Let's find the probability that we have between 80 and 86 successes. Probability of having between 80 and 86 successes. Notice we don't include 80 and we do not include 86. So if we look on a number line, binomial, which is discrete, this would include 81, 82, 83, 84, and 85. It would not include 80 or 86. So remember, when we correct a half unit either to the left or to the right. So if we're looking for the area in between and we don't include 80, we couldn't correct that way because 80 would be included. As we go towards 86, we don't include 86, so we couldn't go to there, because if we go all the way to there, 86 is included. So we'd have to stop there. So in terms of a normal distribution, we would go from 80.5, the half unit more than 80, to a half unit below 86, so 85.5. So with our correction accounted for, this would not include 80, this would not include 86, because those are not included in the binomial. So let's do another. Let's take a look at this one. Get over it quickly. So they ask us several things. To begin, they say, write this binomial probability question. So this is the graph of the binomial probability distribution. The bars represent, just like we did over here, the probability of each of these. So this is the probability of 6 successes, 5 successes, and 7 successes. So we're looking, what is the probability that X is between 5 and 7 and includes those? So that's the first part of the question. It's the probability of 5 plus the probability of 6 plus the probability of 7. Then it wants us to actually do that calculation. Well, remember, since this is binomial, we have a whole formula for that based on N, P, and Q. Remember, Q is the complement of P, so 0.6. That formula generically is N choose X times P to the X q to the n minus x. So for x equals 5 and n equals 16, this is 16 choose 5 times 0.4 to the 5 times 0.6 to the 16 minus 5. Remember, 5 is the number of successes. This exponent is the number of failures. And then we would have to drop down and find the probability that x is 6. So that would be 16 choose 6 times the probability of success 6 times the probability of failure, whatever is left. If there's 16 trials, 6 successes, there are 10 failures. And then the probability that x equals 7, which is 16 choose 7 times 0.4 to the 7 times 0.6 to the whatever is left. 16 trials, 7 successes, that leaves 9 failures. So we have to do each of those calculations. And remember what 16 choose 7 means, or how we calculate that. We do our first number factorial divided by the second number factorial times their difference factorial. And we get a number for that. So for this bottom one, it would be 16 factorial divided by the result of 7 factorial times 9 factorial. So that's 11,440 times 0.4 to the 7th times 0.6 to the 9th. So that's 0.189. So that's just that bottom one. We still have to do this one. So that's 16 factorial divided by the result of 6 factorial times their difference, so 10 factorial. So that's how many combinations. Do that times 0.4 to the 6 times 0.6 to the 10th. And that gives us 0.198. And then this other one, that's 16 factorial divided by the result of 5 factorial times their difference, so 11 factorial. So that's the number of combinations, so times 0.4 to the 5th times 0.6 to the 11th, 0.162. So if we're looking for the binomial probability that x is between 5 and 7, we have to add those 3 probabilities together. So 0.162 plus 0.198 plus 0.189. So about 0.549. And I say about because we did round to the 3 decimal places. So obviously that took a little bit of work to do. And if we had more successes that we were having to deal with or more trials, it would take a while to do all of those calculations. So instead of doing all of that, since n times p and n times q are both greater than or equal to 5, you can do n times p, that would be 6.4, and n times q, that'd be 9.6. Both of those are greater than 5, so we can use the normal distribution to approximate this. So first we have to figure out what are we going to convert that to in terms of a normal distribution. If we're going from 5 to 7 and we include 5 and we include 7, if we're doing our continuity corrections, we have to go a little bit to the left of 5 and a little bit to the right of 7 to make sure both of those get included when we normalize it. So in terms of a normal distribution, we're looking for x being between 4.5 and 7.5. Well, what do we do? How do we find a normal distribution after all? So if we sketch our normal distribution, we need to know what the mean is. Well, we know how to get the mean for this. The mean for a binomial distribution is n times p. So if we do n times p, we get that the mean of our distribution is 6.4. We also have to know the standard deviation. Well, what's the standard deviation? The variance for a binomial distribution is n times p times q, and then the standard deviation is just the square root of that. So our standard deviation for this distribution is n, 16, times 0.4 times 0.6. Take the square root. So 16 times 0.4 times 0.6. Square root of that, so let's call that 1.96 is our standard deviation. So we have our mean, we have our standard deviation. We know that we want to be between 4.5 and 7.5 in the x direction, so we're looking for that area. So we have to convert each of those to z values. Remember, z is what we're looking up in the table. So in terms of z, let's convert this. So our data value minus the mean over the standard deviation. So 4.5 minus 6.4. Divide that by 1.96. So about negative 0.97 is this z value. Now we need to find out, well, what is the z value that corresponds to 7.5? So 7.5 minus the mean over the standard deviation. So if we subtract 7.5 minus 6.4, divide that by the standard deviation, our z is about 0.56. So now that we have the z values between which our area lies, then we can find our area. If we look up 0.56, remember that tells us all of the area to the left of 0.56. And then if we look up negative 0.97, that tells us how much extra is included. So we just subtract those. So let me pull up a normal distribution table and we'll look up those numbers. Okay, so if we look up a z value of 0.56, 0.56 has an area of 0.7123 to the left. That's going to include this much extra, so we're going to take off that area. So if we look up negative 0.97 for z, let's see, here's negative 0.9, here's 7. So the area that's included in that left tail that we need to get rid of is 0.1660. 0.1660. So if we subtract those, 0.7123 minus 0.1660, we get about 0.5463. very close to what our actual area was. This is our actual probability that we got from finding those probabilities. This is the area under that normal curve, which is an approximation of our probability. So in this case, it took about the same amount of time to do each one, but imagine that we had 50 or 90 or so of these bars that we had to add together. We wouldn't want to have to do the binomial formula 40, 50, 90, 80 times. We could convert it into a normal probability, use what we know about normal distributions, and find the area as an approximation. Once we converted it to our probability in terms of a normal distribution, one of the keys was we had to know the mean of that distribution. That's just what was the mean of the binomial. We also had to have the standard deviation. That was the standard deviation for the binomial. Mean and the standard deviation for our normal distribution, we can normalize it, and we can use those values to get our probability.